Next example we have here is example 2, where we are to use Stokes' theorem to show that the line integral of this vector field over C is 0. So let's go ahead and take a look at this. So they're giving us a path in 3 dimensions. So we've got 3, 0, 0 to 0, 2, 0, and then up to 0, 0, 1. So this looks something, and then back to 3, 0, 0. So this is our path, and then of course we have the x-axis. Something like that. Y-axis. So x, y, and z axes. And there's our path. So this is 3, 0, 0. This is 0, 2, 0. And this is 0, 0, 1. Okay. So if we think about what we would have to do to actually calculate this, because this is saying to use Stokes' theorem. So if we're supposed to use Stokes' theorem to show that this line integral is 0, they don't actually want us calculating this line integral directly. Because if we do, we're not using Stokes' theorem. Stokes' theorem is a way of relating a line integral around the boundary of a surface to the double integral of something, the curl of f, over that surface. So we actually want to calculate the double integral here. So let's go ahead and say that our domain D is this enclosed triangular region. And then we already have the boundary of D oriented. So there we are. So really this C in the problem right here, this line integral over C, this C is exactly the same as the boundary of D. So ultimately, we want to calculate the double integral over, actually, let's call this S. Sorry, doesn't actually matter, but I'm going to keep defaulting to S. The reason why I called this D is because this is a flat this is a flat domain, so I usually call flat things D, and things that are not flat S in general for curved versus non-curved surfaces. So I will ultimately flip back to S at some point, so let's just go ahead and call that S. So this is the double integral over S, the curl of f dot ds. Well, the curl of f, if we actually take the curl of f, so the curl of f, let's just get that out of the way. The curl of f ends up being 0, negative 4x, 2x. That is the curl of f. Okay. So the reason why using Stokes' theorem is nice here is because if we didn't use Stokes' theorem, we'd have to parameterize this path, call it C1, parameterize this path, call it C2, this path, C3, then the boundary of S, which is C, is really C1 glued with C2 glued with C3. So then if we did the line integral over C, we'd actually have to do the line integral over C1 plus the line integral over C2 plus the line integral over C3, which means we need an R1, an R2, an R3, and you get the idea that it's a lot of work. Let's not do that. So instead, the surface integral can be easier. Okay. So in order to do this, we're going to have to, whenever we're doing a surface integral, we're going to need to parameterize the surface itself. Okay. So what we can do here is, well, the easiest way to parameterize this surface, I imagine, would be to get the equation of this region here. Because this is not a plane, because a plane is infinite and it goes on forever, but this is a portion of some plane, right? There is some plane, and this is just some triangular region of that plane. So what we want to do is figure out what is the equation of the unique plane in which this region lies. So what we can do here, we can think back to chapter 12, where we were given 3 points and asked to determine the equation of the plane containing them. Okay? So let's go ahead and call these points P, Q, and R. Then we can go ahead and say the vector, let's say the vector P to Q is the vector, let's see here, what would it be? It would be 0 minus 3, 2 minus 0, 0 minus 0. We'd have the vector, let's say, P to R. Oops, let's put arrows on those. The vector PR would be 0 minus 3, 0 minus 0, and 1 minus 0. Then, if we do PQ crossed with PR, this should give us the normal vector to the plane. So the normal vector, if we actually do this cross product, is 2, 3, 6. Okay. So then we have a normal vector, 2, 3, 6, and we have knowledge of multiple points on this plane. So let's go ahead and just go ahead and come up with the equation of this. So we can use the point R. So if we do this, we'll have 2 times x minus, well, the x coordinate of the point, so 0, plus 3 times y minus the y coordinate of our point, so 0, plus 6 times z minus 1 equals 0. So now we can go ahead and simplify this. 2x plus 3y plus 6z equals positive 6. I'm just going to distribute the 6 to get negative 6 on the left, and then add it to get 6 on the right. So we have that. And now we're free to solve this any way we want to. Really doesn't matter. I'll just solve it for z. So z is this is 1 minus 2, 6, so 1/3, x, minus 3, 6, so 1/2 y. Okay. So what we could completely do at this point is we could parameterize this, say, using, we could do the whole shortcut trick that we talked about, where we can even use the same variables. I know that I almost always use use u and v, but we can just keep the same variables, because if we're going to let x equal u and y equal v, might as well just let x be x and y be y. And then here we get 1 minus 1/3 x minus 1/2 y. Sometimes introducing new variables is more confusing for some people, so let's try it this way. I don't usually do it this way, but it's fine. And in a previous video, we talked about how whenever you parameterize something like this, so if you have, let's say so z equals a function of x and y, you are always free to parameterize it like this, in which case your normal vector, right, depending on how you cross them, your normal vector is effectively going to be negative fx, negative fy1, or if you do it in the opposite order, ry cross rx, this would be fx, fy, -1. Okay. So if we actually go through this, to get this, we would see that Rx cross Ry would be equal to negative this would be the x partial of our function f right here. So the x partial is -1/3. So this would be +1/3, negative -1/3. This would be negative -1/2. And then this would just be 1. Okay? So that is a normal vector. Now this vector here is pointing upwards because this is a positive z component. So notice here that what should our normal vector actually look like over here? Is our surface oriented, should our surface be oriented upward like this, or should it be oriented downward like that? Well, think about this. Remember that we talked about how an orientation on the boundary determines an orientation to the surface. So if you think about this, consider on this boundary, that's our orientation. So if we think about moving to the right and moving down, if we start by outward crossed with the assigned orientation, so if we do this, this would produce a normal vector pointing kind of up like that, or out of the screen. Depends on your perspective here, but we're crossing like this. So this would give us an upward pointing normal vector, something like that. So here I'm going to go ahead and just say something like that. So upward pointing normals. Okay. So this has got a positive x component, so this is upward, so we're good. So with that, we can go ahead and begin our process here. So the double integral over S curl of f dot ds is equal to, this would be the double integral over d. We're going to take the curl, which is right here, and then we're going to, this is where it can be a little confusing for some people. Normally what we do is we replace x with whatever the x component is of our parameterization. Well, the x component is x, so x gets replaced with itself x, so x remains x. So this just becomes the same thing. 0, -4x, 2x. We're going to dot that with our found normal vector here, which is 1/3, 1/2, and 1. dA. So this is the integral, double integral over d. If we do our dot product, we're going to have the following. This will be, parentheses, this will be 0 minus 2x plus 2x dA, which is equal to the double integral over d of 0. And no matter what d is, we're going to get 0, because the integral of 0 is 0. So that checks out. There is another little thing here that we could have done that's a little bit slick. I like this. So instead of having to worry about all of this stuff here, all of this stuff here before going to here, let's go back a second and show you all another way this can be done. That will save a lot of time, but it is dependent upon your understanding and knowledge of the definition of a vector surface integral. So remember that a scalar surface integral was of the form double integral over S. We had some scalar function, ds. And the way we calculated this was the double integral over d, where d is the parameter domain for the parameterization that generates S, f of r of uv, the parameterization. And then here we'd multiply by the magnitude of the cross product of the partial derivatives. Okay. Well, a vector surface integral defined similarly, this is f dot ds, which is really defined to be the amount of the vector field that is in the normal direction. It's the amount of the vector field f that's in the normal direction to the normal vector of S. So in a way, a vector surface integral is just defined to be a very specific scalar surface integral. Okay? So here, let's actually go ahead and let me rewrite something here. Let's make this a capital N. Okay, so then I'll say this is a unit normal vector. Okay. So, what do we know? Well, we do know that for a given, so this right here is some scalar function, right? This is a scalar quantity now because the dot product of two vectors is a scalar. So what we're integrating here is now a scalar. So we can think of this as the same as, we can think of this as the same as right here. So if we were to go ahead and compute this, like this line says to compute, we would take our integrand and replace it with f of our parameterization. So this would be our f but here this is going to be written in terms of r of uv, so I'm just going to go ahead and put this like that. It's a little bit weird, but whatever, it works. And then ds is the magnitude of the cross product, dA over d. Well, here's the thing. What is this dot product? Well, we do know that a dot product can be expressed as the length of f times the length of n, and then this is now just a function. This whole thing is a function of u and v. And then this gets multiplied by this. Okay? So this n right here just needs to be a unit normal vector. Well, what is a unit normal vector? A unit normal vector is just a normal vector to the surface, which is this, right? Divided by its own length. And we're taking the magnitude of n. So we have like this. So notice here that we have a copy of the magnitude of RU cross RV in the bottom and we have 1 at the top. So if we make this replacement of this n with this quantity, then we can cancel this in the top with this in the bottom. In which case, this whole thing boils down into the double integral over d magnitude of f times the magnitude of RU cross RV. There's one thing I forgot to list here. That's my bad. Right here, there should be the cosine of theta here. Excuse me. I guess if this were in the correct order, it'd be something like this. Sorry about that. So that's a lot of, oh boy, that's a lot of stuff. That's a little bit too much detail. Let's just go back to what I really wanted to say here, which is effectively this. The double integral over S f dot ds can be written as the double integral over the double integral over S of f dotted with lowercase n, let's say now, ds, where this n is any normal vector. Believe it or not, you can actually use any normal vector here. So the length of the vector could be anything it wants to, because in this case, it gets canceled out with this. So in particular, what we could do is use this fact right here. We can take our normal vector, or excuse me, our vector field, 0, -4x, 2x, and we could dot it with the normal vector we found to the plane. Right here. And this would give us, essentially, the double integral over S, -12x plus 12x ds, which is 0. So this would save us the time because we wouldn't actually have to parameterize anything. We could have just dotted with this normal vector and saved all that time. Either way you do it, it works out.